Welcome everyone to Structural Analysis 1, an elementary course in the analysis of determinate structures. Today is the 12th week and it's the last week of this online problem solving session. So in the last couple of weeks, we were studying about all about strain energy and how we can use this concept in deducing deflection and slopes in different types of structures like trusses, beams, and frame members. We have seen in couple of weeks a lot of different formulations. One of the biggest formulation was the virtual work method and strain energy method for computing the deflection and slopes in these structures. Continuing the same topic, today we will be having one more concept that we will be studying today for getting the deflection and other deflection and slope. In today's lecture, we will be studying about one of the famous theorems in structural analysis elementary course, that is Castigliano's second theorem. We will be first seeing what this Castigliano's theorem is. Later on, we will solve a numerical problem on this and see how we can use this concept for the deflection of beams, or we can use it for both frames as well as truss members. So Castigliano's theorem, actually this theorem was put forward by Alberto Castigliano in 1873, and it's commonly known as Castigliano's second theorem. It was put forward by Alberto Alberto Castigliano in 1873. Okay, 1873, and it's commonly known as Castigliano's second theorem. Actually, okay. So Castigliano's first theorem, which that is actually regarding the establishment of the equilibrium equation for the structure, and that we will not be discussing here. The only important theorem for us right now is the Castigliano second theorem. So this theorem, actually, the statement of this theorem goes like this. It states that for linearly elastic structure, the partial derivative of strain energy with respect to an applied force or applied couple is equal to the displacement or rotation in the force or couple along the line of its action. In simpler words, what it says that if we have a structure and it is deforming within elastic limits, that is loading is proportional to the deflection caused, and if at a loading position, if we compute the strain energy of our structure and took the partial derivative of that strain energy with respect to a particular load, we will get the partial derivative of that strain energy with respect to that particular load will give the deflection in the structure in at the point where the load was acting, and that deflection will be in the direction of the acting load. Or in the terms of moments, we can say that if we take the partial derivative of the total strain energy of the structure respect to a particular moment acting on our structure at a particular point, it will give us the rotation at that point, and that rotation will be in the direction of the acting moment or couple. So this is very simple, and hence we can write the mathematical forms of this uh, Castigliano's second theorem as, if we treat U as strain energy of the strain energy system, what he says that what you have to do is only take the partial derivative dou U by dou P. What you will get from this dou U by dou P, you will get deflection at point of ACTI action of load P, and in same direction. Okay, same direction. And another thing in this is, if dou u is the strain energy of our system, and we take the partial derivative with respect to a particular couple acting on our structure at a particular point, what we will get? We will get slope, rotation, rotation at point of action, at point of action of couple m bar, and in same sense. Okay. What it means, that if the couple was acting in clockwise direction at a particular point, and we took the partial derivative of strain energy with respect to this couple, our rotation or slope will be also coming in clockwise direction, and vice versa. So what we have to do is, we have to do things like this. For example, this was our for example, one of the basic structures in structural analysis we study is this. For example, this was our structure, and like this, for structure we were having different loadings acting. Okay, like w of x, we can say that we have loads acting pi at some I point. We have loads moments acting like this, mi sorry, mj at some point j. What Castigliano's theorem states that, Castigliano's theorem states that it states that it says that obtain strain energy, energy of system. You do the first step, obtain strain energy of system. Okay. Second step is take partial derivative derivative with respect to either pi or mj, with respect to pi or mj. What you will get finally? Finally you will get deflection. So we are getting it a result, and we will get deflection and rotation, rotation at I and j in our structure. I have simplified this theorem for you in term of this flow chart. Okay, so the flow chart goes through like this. We did one step like this from our structure like this, and then we move to this step. Okay, and this whole thing we can term as, this is from this to this point. Okay, this we can term as this thing. Okay, this is actually this Castigliano's second theorem. This is our structure our under consideration. So I hope this concept is very clear to you, because it's important to understand what is the basics behind Castigliano's second theorem. Now we will be deducing its formulation, how actually this is true mathematically. So for that we will start doing some mathematics and see how actually this is true for a structure. For that I will need this figure. So for that, if I assume a linear elastic structure like this, it's a simply supported beam subject to 3-point loads P1, P2 and P3, and these 3-point loads are causing deflections theta 1, theta 2, theta 3 at their respective points of action. And deflection caused, I will tell this first hand, that deflection caused, that is theta 1, theta 2 and theta 3, are independent of the sequence of application of P1, P2, P3. That is, if P2 is applied first and then P3 is applied, on again delta 3 deflection will be caused at point 3, and it will not be affected by the manner in which P1, P2 and P3 will be applied. So because this is a very important statement while reducing this equation. Then we have for this, we can also assume that these P1, P2 and P3 are applied gradually. That is, they increase from 0 to their final values, such that the relationship between P and delta, that is load and deflection, is linear. So this is important to write here, that P1, P2 and P3 are gradually increased from 0 to final values. Okay, final values, such that P delta relation remains linear. Okay, sorry, remains linear. What I mean by that is that, for example, if this is P delta curve, it is P, this is delta acting here, not delta, that relationship between them is linear. P is increasing linearly, and the strain energy will be just the area under this P delta curve. Okay, this will be area is equal to strain energy stored. I have told this concept in the very beginning of this chapter, that area under the P delta curve is the strain energy stored in our system. So we can write the strain energy for this type of loading as U to be equal to that is actually the work done by the external loads. As I already told, the relationship between the work done and the strain energy in the last lecture, 1/2 of P1 delta 1 plus 1/2 of P2 delta 2 plus 1/2 of P3 delta 3. Okay, delta 3. Okay, And I already told you delta 1, delta 2, delta 3 are the deflection of beam at the points of application of P1, P2, P3 respectively. Okay, delta 1, delta I going from 1 to 3 are deflections caused at applications at application of PI. Okay, that's clear. So from the above relation we are able to see that U is a function of P1, P2, P3. Okay, P3. Okay, so if we treat this equation as 1, okay, this equation is 2. Everybody able to understand? This equation is 2. Okay, then what we are going to assume is that the deflection delta 2 of the beam at the point of application of P2, we are assuming that now we need to determine the deflection delta 2 because of the application of point of P2. And what we do is that we assume that P2 is increased by infinitesimal amount delta P2 such that the increase in the total strain energy is delta U. So we assume that, okay, I will erase that. Assuming delta 2 because of P2 is desired. Okay, desired, and P2 is increased by small amount dP2. Therefore change in strain energy will be, okay, change in strain energy will be du, total change in strain energy from the partial derivatives. We can say that du will be dou p. It is total strain energy dou partial derivative of strain energy with respect to dou p2 dp2. Okay, so this way you will treat as third. Okay, we have this third equation. Now the total energy of system will be total energy will be after increasing P2 by infinitesimal amount dP2, okay, will be U plus UT. I will denote it as, it will be U plus what will be the small incremental change in strain energy du, and du is actually equal to dou U by dou P2 dP2. Okay, we'll treat this equation as equation 4. Okay, uh, as I already told that beam is assumed to be linearly elastic material, so it will be independent of the sequence in which the loads are being applied. That is P1 and another load now is P2 plus dP2 and another load is P3 and are applied. And the total strain energy in the I mean to say total strain energy stored in our beam should be same as it was already. So we are assuming linear elastic behavior. So total strain energy if after dp2 is added will be same. Okay, okay, this is clear. Now we will consider one sequence. In this sequence, we will say that dp2 is applied to the beam before the application of p1, p2, p3. So now our beam is there. There is no p1, there is no p2, there is no p3. So our beam is now like this. Okay, now consider beam like this, and sorry, I will write this one completely. Assuming linear elastic behavior, so that total strain energy after dp2 is added will be same irrespective of sequence of application of p1 applied. Now p2 becomes p2 plus dp2 and p3. Now what we are assuming that we are firstly applying only dp2. Okay, dp2 applied first, and in addition after that dp2 we are applying another loading, not another loading, what actually was loading there. Okay, or applying this, we are just replace returning the original loading to our structure. It was, as I see shown in the figure, it was p1, it is p2 in the same direction of the p2, and it's p3. Now it will be very easy for you people. So first it will be very small deflection, caused by, it will be very small deflection caused by dou p2, and it will be good amount of deflection caused by these three loads. Okay, so since this is a elastic curve, we need to match it, show this dotted line, elastic curve of line. Okay, we need to show it by this, and this can be also done in a similar fashion. Okay, these are our things, and this is causing d delta p2 deflection here, delta 2 deflection here, d delta 2 deflection here. Okay, and these were already causing their respective deflections as uh, delta 1, this was causing delta 2, this was causing delta 3. I hope this concept is clear to you. Okay, so now when we combine both these systems, sorry, so we will write total strain energy of this loading sequence, strain energy of this loading sequence. So what will be the total strain energy now? ut will be again, so you have to calculate all the strain energy that will be caused. Okay, first the strain energy of this system. Okay, it will be, I again told you, dp2 is applied gradually, increasing from 0 to dp2 linearly, so that relationship between dp2 and d delta 2 will be linear. It will be 1/2 of dp2 multiplied by d delta 2. Okay, d delta 2, very easy so far. Then there will be the, now again d delta 2 is the deflection already caused, and now p2 is again acting at that point, so it will cause a strain energy of or it performs a work of P2 times d delta 2. So I want to remind you here that why I didn't wrote one half of here, one half of coefficient is not written here, huh? So I will tell you the reason for that one is that because d delta 2 was already caused by dp2. So during the application of p2, d delta 2 remained constant. So no need of one half a factor. So I will write d delta 2 constant during application of P2. So there will be no one half a factor, and then we will be have one half a factor for all the other things, half P1 delta 1 plus half P2 delta 2 plus half P3 delta 3. Okay, P3 delta 3. So we have this type of equation. So we can write this one ut again. Ut will be equal to, if we will see this half P1 delta 1, P2 delta 2, P3 delta 3, it is initially equal to, this is initially equal to u. If we take the equation, which equation first, it is equally equal to u. Okay, from equation first. Okay, so we can write ut to be equal to 1 half of dp2 d delta 2 plus p2 d delta 2 plus u. Okay, this is clear to you guys. So now uh, so sorry, I wrote here wrong. It is dp2 times delta 2 because dp2 is being applied. Okay, this is dp2 times the deflection that will be caused because of the application of load p2 will be delta 2. So there will be no half factors because dp2 actually remains constant. D dp2 remains constant, and during the application of p2, which causes deflection delta 2. So dp2 delta 2, it will be dp2 delta 2. Okay, sorry for the mistake. dp2 delta 2. So we can say that this is like this, and if we ignore these are the dp2 delta 2 will be very small because both are small quantities. We can approximately put them equal to 0. We will have our ut term to be equal to total energy. Ut will be equal to dp2 delta 2 plus u. Okay, dp2 delta 2 plus u. Now this is one thing, this will be our equation 5. Okay, we'll do one thing, we will take equation 4 here, we will take equation 5 here, and both, as both are equal, left hand sides are equal, we can equate them. Okay, so we can write equation 4 and 5. From 4 and 5 we can write u plus dou u by dou p2 dp2 is equal to dp2 times deflection delta 2 plus u and u will get cancelled, or by rearranging we can get dou u by dou p2 partial derivative of u with respect to p2 will give us delta 2, which is actually the mathematical statement of Castigliano's second theorem. mathematical form of Castigliano's second theorem, CST. Okay. Hope this concept was clear to you. Now we can see its application of Castigliano's second theorem. How can we apply it for the deflection in trusses, beams, and frame structures? Okay, so we can for the application to the trusses. So in trusses, in trusses, this strain energy is given as, okay. We saw that in last class strain energy was given as U will be equal to the summation of strain energy of all the members, where it was given as F square L by AE. F was the member force, and that FL by E was a deflection in that member. So it comprised of F square L by AE. Sorry, F square L by 2AE, because there will be the factor 2. So as per Castigliano's second theorem, as per Castigliano's second theorem, deflection delta in truss will be, we can write deflection delta in truss, delta will be equal to partial derivative of this strain energy dou by dou p at that point, okay, summation of total strain energy of all members F square by 2AE. This is clear. Okay, then we can take the summation outside. We can write delta to be collectively equal to F square. Its derivative will come, it will cancel the 2 and it will give us dou F by 1 dou P. It will give one term like this. It will give another term dou F by dou F by dou P. Sorry, not another term will be FL by E. Okay. So this will be the deflection as per Castigliano's second theorem in our truss structure. Okay. It is very similar to the expression of the method of virtual work. If you people can see that we have the same thing. We have F virtual divided by F real divided by times FL by A. Okay. This was the same thing here there also. Now, in application to the beams, we know that in beam members we had this strain energy given as in beams. Strain energy is given as strain energy. What is the strain energy in beams? We studied that strain energy U will be as 0 to L. We have to equate m square by 2EI. Hope you remember this expression dx. We have to integrate this expression. So if we need to find the deflection, so uh, as per CST, deflection delta will be given as, we have to take the partial derivative with respect to application without respect to load. So delta will be given as dou by dou p of, okay, dou by dou p of 0 to L m square by 2EI, okay, dx. So if we will solve this expression, delta will be equal to taking the integral outside 0 to L, 2 and 2 will be cancelled. It will be dou m by dou p, first term m by E, okay. It's again equal, similar to the expression given in virtual work, m by E dx, where that was m v m times E divided by E. So it was deflection. If you people need to compute the this rotation, then again theta will be given, and you have to only take the partial derivative with respect to applied couple. So I am denoting that with m bar to differentiate it with the given the moment inside the beam m applied couple. Okay. So again we have to take the partial derivative, then theta will be straightforwardly written as 0 to L dou m by dou m bar. Okay, m by e, very simple, dx. So this is for deflection, this is for rotation. Okay, hope you people got these concepts. Now again there is one same story happening here. We have to apply the same concept to the frames. As I already told there, in frames strain energy is composed of axial strain energy and bending strain energy. The same two things is here. This axial one and bending one. This is bending. Okay. Now combine these two deformations because of axial and bending, you will get your thing for this in frames. Okay. So application to frames, I again told you what you will get, the total deflection by combining the total deflection delta will be delta axial plus delta bending. Okay. And these delta axial and delta bending will be as per Castigliano's second theorem that we already studied. So we can directly write our delta as the summation of these two things. First axial was summation of dou f by dou p times f by ae, fl by ae in fact. Okay. And then we have to take the summation in the frames because there will be large number of beams. Summation integral again dou m by dou p m by ei. Hope you are able to understand this concept. It's very easy in frames because it's just the application of combination of truss and a beam member. This is this one. And same for the rotation. For deflection, okay, we have to write for rotation. For rotation again, theta total in our this will be theta axial plus theta bending as per CST. So we can directly write theta for our frame member as summation. We have to take the summation. There are large number of numbers. Dou f by, we have to take the partial derivative with respect to the applied couple dou m bar. Okay. Again m bar I am using here. Fl by ae, and for beam it will be summation of all the beams, partial derivative of all the beams. It will be dou m by dou m bar m by ei dx. Okay. This will be deflection. This will be deflection. Deflection at point of application of P. Okay, clear. This will be rotation at point of application of M bar. Again, I told you that in beams, axial deformations of the members of frames are negligible. Okay, So if they are negligible, then you can just ignore the actual terms. You can directly write deflection as summation integral dou m by dou p m by ei, okay, times dx, and another you can write theta as summation integral dou m by dou m bar m by ei, only when bending deformations are considered, because actual deformations are very negligible. We have this, we have bending much greater than actual effect, okay. Hope this formulation was very clear to you. I first derived the Castigliano's theorem, its formulation, and then I applied it to all the three structures, that is trusses, beams, and frames. Initially, the in trusses we only needed the strain energy. Then in beams again we only needed the strain energy, and we took the partial derivative in trusses with respect to applied load, and in the beams we took the partial derivative with respect to applied load or applied couple to get the deflection or the slope at a point. And then in beams to and then take this Castigliano's second theorem, its application to frames. We have to just club the truss concept and the beam concept together, because it's just the combination of the axial effect and the bending effect. We just saw how we can get the deflection at a point of application of P by taking the partial derivative of strain energy in axial and bending domains, and same the rotation by taking the partial derivative of axial strain energy and the bending strain energy with respect to the applying moment m bar. And if the actual deformations are neglected, then we have to discard the terms which are uh, representing the actual effects in our these deflection and rotation formulas. I think this concept was clear to you, and now this will be more clear to you when I solve a numerical problem over this. So for that, we have to determine the deflection of a point C of a beam as shown in the figure. Point C is this, and a load of 12 kilonewton is acting at that point. And I have to use the Castigliano's second theorem. So if you people remember the same beam, we analyze it using moment area, the conjugate, and the virtual load methods. So now we are using it using a fourth method in the determination of the deflection. What will be the procedure, since 12 kilonewton is the external load applied and it's already acting at point C. What we will assume that this P is some unknown load P. This 12 kilonewton is some unknown load, and we will term this, we will use 12 kilonewton to be equal to some unknown load P, okay. We'll assume this thing, okay. Assume this thing. With the inclusion of this P load in our structure, what we will do our structural analysis of our structure by computing the support reactions, computing the support reaction, and then computing the moments in the whole beam. After that, we will compute the strain energy of our beam structure with P as unknown. When we did all these computations, then we will take the partial derivative of our strain energy with respect to this P load, wherein we will get a long expression in which P will be unknown. After putting the values of after doing all the computations, wherever we will get the P value, we will have to put the value 12 kilonewton at that point, and we will get the deflection at point C, because it is actually we are computing the deflection at point C. So we have to just take the partial derivative of the strain energy of whole system with respect to this 12 kilonewton load. So we can take the partial derivative with respect to 12 kilonewton only if we assume this to be a variable, okay. So this is the total formulation for this. So what I can say that calculate. So we will be assuming P to be equal 12 kilopound. Okay, let's keep the units in these kilopound and kilofeet only. Then second point is calculate strain energy of beam. Do take derivative, and in more precise sense is the partial derivative of, so this is u, take partial derivative of u with respect to p, and we will get deflection at point C. So this is the flow chart that we will be following. So if we assumed this, then we went on to this step, then we took the partial derivative. In each and every problem regarding the Castigliano second theorem, you have to follow the same methodology. Okay, so this process will follow on this process, this process will follow on this process, and this process will follow on this process. Okay, hope this is clear to you. And one more thing I want to mention here, that we have to use the same table formulation that we use it in all the virtual work and strain energy problems. Okay, so first I will draw the free body diagram of our structure is like that. mm, so first let me just put it like this so that we can move on to the next page. Okay, so our structure, free body diagram of our structure will be like, this is again our beam, and on this 12 kilonewton is acting at up to point B. Okay, it is 12 kilo pound per feet, and these are points A, this is point B, this is point C. Okay, this is point C, and this was actually we assumed that load P is acting here. So because of this point, if I do the analysis, I will get a reaction of, 30 minus P by 3. Don't tell me how I got this reaction. This is very easy to, you can compute it on yourself. Okay, and here I will get a reaction of, these reaction computations from the basic things, 30 plus P by 3. Okay, if we, if you check the equilibrium also, it will be satisfying. Okay, listen, we got it. We will now again in the strain energy computation form for problems and other virtual work problems, I told you to break your structure in different segments depending upon the loading condition and the boundary conditions. So for the convenience, because we do this for our convenience, so we will be able to compute the strain energy very quickly by segmenting our structure. Okay, so here I am dividing my whole beam into two segments, wherein I am using one coordinate system from here x up to this point. Okay, one segment will be AB, and another segment I will take as CB, and in which I will take origin as C. Here from this I am changing x like this. Okay, up to this point. So x will be 0 in this case, up to x will be equal to, what is the limit? Limit is 10 feet, because this is, wait, this is 10, and this is, okay, this is, 10 feet here, this is actually 30 feet here. Okay, 30 feet here, so x is equal to 10. So again x will be 0 here, x will be equal to 30 here, this will be for this will be for segment which CB, okay, and this will be for segment this will be for segment AB, okay. Hope you got my point, okay. Now I will do the calculations very quickly. So we have to make the table like this, same table that we were drawing. So we have to just CG segment here. We divided our whole beam into two segments only. One segment was AB, another segment was CB, okay. And then in this we chose this x coordinate. So for that x coordinate, what we did is we choose what will be the origin and what will be the range is the same thing. And we have to compute the moment in each segment because that is the only term in our deflection formula, and we need the partial derivative of that moment with respect to p. You already know that, why I'm telling this, dou m by dou p, and it will be kilo pound feet per kilo pound. Mm, Please take care of the units. Origin will be A, as I already told you. Origin will be C. Range will be 0 to 30. Range will be 0 to 10. Okay. So in this figure, what will be the in this segment? What will be the moment? Okay. In this segment, what will be the moment? M will be equal to, first it will be reaction 30 minus P by 3 times X. Is it clear to you? Reaction this reaction time is x distance, okay, and this, then there is downward load, it is 12 x times x by 2, okay, 12 x square by 2. Hope this is clear to you. Okay, so this is not 12, this is 2, sorry, this is 2 kilo feet per 2 kilo pound per feet, okay. So it will be 2 and 2 will get cancelled, okay, is x into x. So this will be, sorry, this is a red pen. This will be 30 minus p by 3 times x minus x square. If you take the partial derivative of this with respect to p, what you will get? It will be equal to minus x by 3. You look carefully. Okay. And for this, the moment will be, for this region, moment will be p is acting like this, and this is this. This moment will be clockwise. It will be minus px. Okay. So we will write minus px here, okay. So our partial derivative will be minus x. Very easy. So we will look at these terms in our computation, deflection computation formula, okay. So then we will leave it like this. So we got our point. Now deflection at C can be determined by substituting P is equal to 12K in the equations of M and DMP, okay. Now you people see here, now deflection delta c you delta c will be equal to 0 to L as per Castigliano second theorem, dou m by dou p times m by ei times dx. And what we have to do is substitute p equal to 12 kilo pound everywhere, okay. So this thing we have to do in this formulation, in this whatever we will be getting here. So since our beam is segmented in two parts, we will write the moment for each part, and 1 by ei is constant, so we can take ei outside. We have to write the long expressions for our integrals. First range is 0 to 30, Dou p dou m by dou p. Dou m by dou p is x by 3. Okay, minus x by 3 in fact. Okay, minus x by 3. And what is the expression for m? M is 30 minus p. We have to put p equals 12 kilopound. Okay, it is 30 minus 12 by 3. 12 by 3 times x. Okay, x minus x square. Okay, this is whole term like this. And ei is already taken outside, it's dx. And another term is 0 to 10, range is 0 to 10 here. 0 to 10, our m is minus px, so it will be our dm by dp is minus x. And m is minus px, so it's minus 12 times x dx, and the integral is closed here. So when we will run this integral, we will see, we will be getting minus 6 comma 500, uh, and units will be kilo pound feet cube divided by ei. Okay, and ei will be having units of kilo pound feet square. That's why we will get feet. Then we will get 6 comma 5400. This will be again 8 kilo pound, and we have to convert feet into inches. It will be 12 cube. Okay, because 1 feet is equal to 12 inches. 12 cube divided by, what is the value of ei? Ei is 29,000 kilo pound per inch square, and I is actually equal to 2000 inch power 4, and it is inch cube. Okay, so it will be our deflection will come out to be equal to minus 0.194 inch. So actually we are getting a negative deflection, so that it means that the point C deflects upwards in the direction opposite that of P. P was assumed to be applying downwards, but the deflection will be upwards. Okay, deflection will be upwards. So we will get delta C to be equal to 0.194 inch, and it will deflect upwards. Okay, like this. This will be the deflection of our structure. It was like this. It was like this initially. So there was a huge uh, distributed load acting over it at this point. So it will bend like this, and will be deflection will be upwards. Delta C. Okay. So okay. So I think our time is over. So thank you for joining. Okay. So as this was our last week of interaction, thank you everyone for joining these live sessions. Hope you have got something from these live sessions, as I tried to as I tried my best to teach you the basic concepts again, because these concepts were already discussed in the online lectures that are being posted on NPTEL site. By it, I again uh, try to explain these concepts for the numerical problems that we were discussing in the live sessions. I thought that it will be better if I first discuss their theoretical background and then solve the numerical problems. Hope you people have got something from this lecture series. Thank you everyone.